Welcome to Peninsula Seniors Out and About. Today we're at the Western Museum of Flight in Torrance for one of their celebrity lectures. Let's go see what Cindy has for us today.
Welcome to the Western Museum of Flight. I'm Cindy Maka, and I'm the director for the museum. Unmanned vehicles have played such an important role in today's military and law enforcement that it seems appropriate to take a look back at the origins of this fascinating technology. And today, Barry Tyson will help lead the way. Ladies and gentlemen, Barry Tyson.
Thank you, Cindy, and thanks to the Western Museum of Flight for giving me this chance to talk about this time in our history that people must have forgotten about because they never see it anymore. My first slide shows a picture, an advertisement that was run in Aviation Week in January of 1972. I kept that issue of Aviation Week because it shows Ryan's first family of unmanned vehicles, back then called remotely piloted vehicles, RPVs. I'm going to talk a little bit more about RPVs because they're everywhere. You read about it. Every time you open up a newspaper, somebody is talking about drones. This article in the Wall Street Journal last March talks about drones with stealth technology. Recently, we've all read about the Lockheed drone, the Sentinel, that came down in Iran, and we're worried that some of our stealth secrets will be given away to the Iranians. They're now talking about drones that might take off and land on aircraft carriers. And lastly, drones that will do mid-air refueling. A lot of people think Israel was the first to deploy unmanned air vehicles or remotely piloted vehicles. And the article from the AIAA magazine, Aerospace America, says that Israel was the first to send RPVs into situations where a pilot's life it was too risky to risk the life of the pilot. It said Israel introduced the concept of using unmanned vehicles for reconnaissance in the 1980s. And I have the question, what role did Ryan play in the development of unmanned aircraft? Now, when I was working at Ryan, most everything that I'm going to show you was classified, some as either secret and some as top secret. And I was amazed to find when I researched for this paper that all of this is available now on the internet. So I trust I won't be going to jail for revealing this information. Now, looking around, I think most of us remember what happened in the 60s and 70s, but I'm just going to highlight a few points. You might recall that in May of 1960, Gary Powers was shot down over Russia flying a U-2. Today's newspaper, by the way, say that they're nominating him for a Silver Star because of secrets he kept under Russian interrogation. Dwight Eisenhower was terribly embarrassed by that incident because the CIA told him to not acknowledge it, and Khrushchev, of course, came to the UN, made a big issue of it, and Eisenhower said, we're not going to fly over Russia again. You know, one embarrassment is enough. In the fall of '62, observing construction of SAM missile bases in Cuba, another U-2 was shot down by a surface-to-air missile. In '64, under LBJ, the administration was worried about Chinese intervention into the Vietnam War. You might remember the Gulf of Tonkin incident, which prompted LBJ to escalate bombing and also promoted the need for more communications monitoring. In January of '68, the Pueblo was captured, Commander Booker. It was doing electronic intelligence and signal intercept missions, captured by North Korea. Tremendous embarrassment to the U.S. And in April of '69, a Lockheed Super Connie, an EC-121, was shot down in international airspace by North Korea, and there was a need to monitor North Korea. And of course, later on in '73, with the Yom Kippur War, anti-aircraft missile threats to Israeli F-4 Phantoms from SAM-6s and SAM-7s brought up the need for a better way to take out the radar installations, hence the phrase defense suppression. Going back to 1962, a $1.1 million contract was given to Ryan. Ryan was then building target drones called the Firebees, and we'll show pictures of that a little later. These drones were modified for photo reconnaissance. there was a program which was classified, run by the Air Force, and it was called Big Safari. Funds for that modification came out of Big Safari. So as we go to the briefing, I'll give you an overview of what we're going to talk about. A little bit about me, so you know who I am. A little bit about Ryan. And a little bit about what's happening today. About me. I'm a native New Yorker, graduated from NYU, College of Engineering with a bachelor's in aeronautical engineering. The Guggenheim Institute had a wind tunnel at NYU, which attracted me there. I came out at the age of 20, not even 21, and I joined Douglas El Segundo. Even though I didn't really like thermo in college, they put me in an aerothermal group. And I was very happy to find that had nothing to do with thermodynamics. And instead, I was put into working with the Douglas A4 Skyhawk, integrating the Pratt & Whitney J52 engine into that airplane, and later the TA4E. Things at Douglas were winding down in '65, and I was getting a little restless. I had a phone call from a friend in San Diego who said, "Come on down. There's some exciting work being done down at Ryan." I came on down and decided I would join them. And the program they had just won was for a high-altitude unmanned aircraft called the Compass Arrow, which used a brand-new engine called the J97, built by GE. Later, I was head of systems engineering and chief engineer on an airplane called Compass Cope, which we'll go into. And again, in 1975, things were getting wound down at Ryan, and I'll talk about that a little later, and I joined the GARRETT Air Research Company. So going from as a little fish in big waters at Douglas to a big fish in little waters at Ryan to a comfort zone at GARRETT was kind of the history of my career. And I retired after 22 years at GARRETT, putting in 41 years in the industry overall. A long time. I still can't believe it. The wonderful world of Douglas in 1957. Imagine you're 20 years old, you just got a fresh degree, you walk out into the shop, and here are all these A4 Skyhawks. Some were doing machine gun testing, some landing gear testing. There was the F4D Skyray, which held a time to climb record from brake release to 40,000 feet until the 141 took it away, till the F104 took it away. There was the A3D twin-engine Sky Warrior, and they were doing modifications on the AD5 and AD7s. We had a good engineering department. A lot of you know about Ed Heineman. He was our chief engineer. But I was very lucky. Douglas decided to take the J65 engine out of the A4 and put in the more powerful J52. J52 was developed originally for the Hound Dog missile, and there was some concern by the Navy that it wouldn't perform well in a maneuvering aircraft like the A4. So they threw me into this, doing wind tunnel testing, flight testing, coordination with the Navy, with BUEPs. The most difficult thing was coordinating with Pratt & Whitney. What they knew they liked to keep to themselves, but we were able to work closely with them. And so it was very exciting to watch the air induction system design, compatibility with the engine development program. And that really set me on a 40-year career of working closely with propulsion as the key to matching aircraft to their missions. And again, this came in very handy at Ryan. So let's go back to the 60s. There was a lot of global unrest, which we discussed a little while ago. DOD decided we can't risk any more downed airplanes with pilots. We just can't risk it. So are there unmanned aircraft that could do those jobs? They were looking for experience in unmanned vehicles, unmanned flight control, command control, launch and recovery, low-cost propulsion systems, and a company that could keep the cost of these aircraft down. When drones got to compete with manned aircraft for budget, it was the kiss of death. Of course, the Air Force and Navy aviation departments were run by guys with wings on their lapel. They didn't want unmanned vehicles to compete with their budgets. The missions that they had in mind was photo reconnaissance, and this is before the days of digital photography, so we're talking about reels of film. Signal intelligence, for example, where are those radar transmitters? How do we locate them so we can take them out? Electronic countermeasures, how can we jam surface-to-air missiles? And defense suppression, how can we take out radar sites without risking a pilot? T. Claude Ryan, I never knew until I did this presentation his first name was Two-Ball. I don't know how he happened to get that moniker, but when I joined Ryan in '65, he was coming to work every day. And the highlight of his day was having lunch in what we called the chairman's dining room. And if you were an engineer and were invited into that room, it was generally bad news. You had done something bad. I went there only once. That was when Ryan owned Continental Engines, and I was the guy that picked the Garrett engine for a later program. I got to have lunch in that dining room. Ryan was a very entrepreneurial company. I see outside a beautiful Navion. In 1947, Ryan took a contract from North American to market the Navion trainers all around the country. A pilot named Doc Sloan got in that airplane and flew it all over. Ryan also did one of the first air-to-air missiles. It was a liquid rocket-fueled air-to-air missile called the Firebird, but pay dirt at Ryan came in '48 with a contract to do the Firebee. These drones were launched from the ground with a JATO rocket, went up towing a banner. Machine gunners on the ground would shoot at the banner and develop their skills. Once in a while they would tow a flare pot and a heat-seeking missile would go after it. And if Ryan was lucky, they'd shoot down the drone and we'd have to build another one. We also did some very strange things. I worked with a guy named Pete Gerard. Pete Gerard was the chief engineer and test pilot on the Vertijet. This was an airplane where the cockpit swiveled as it went from vertical to horizontal flight. And the way you landed this thing is you came in on its tail and you snagged a wire that was erected like a goalpost on the back of a flatbed truck. And people who witnessed this said, "My God, what a fantastic pilot and what a stupid airplane." So it never went anywhere. We also did a fan and wing airplane with GE called the XV-5A. We built two. Unfortunately, both crashed. This was an airplane to rescue a downed pilot. It would drop a harness, the pilot would get into it, and it would lift it up. And during one of the demonstrations, the harness came up, went right through the fan rotor, and killed the GE test pilot, and the program ended. Now, the real secret to Ryan's success were the unmanned vehicles. In '59, Ryan did an unfunded study looking at the Firebee modified for reconnaissance missions. Then there was the Gary Powers incident in 1960, and the Air Force gave Ryan $200,000 to do a study at what could be done to modify the drone. In '62, Big Safari gave Ryan $1.1 million to modify 4 Firebee drones to do photo reconnaissance. These drones were taken to Holloman Air Force Base, dropped from C-130s and demonstrated. They were found to have very low radar signature, very low infrared signatures. The program was successful. In 1964, the code name for these drones was called Lightning Bug, and they were deployed to Okinawa for flights over China. I understand one of the internet articles said that these drones were given Taiwanese markings, so China, PRC, would think they came from Taiwan. On the other hand, there were pictures of the Chinese parading these drones that were shot down with American markings, so I don't know really what happened back then. Now let's go back to the Vietnam War. Remember what was happening from 1965 to 1975, which by coincidence were the 10 years I worked at Ryan. Operation Rolling Thunder in 1965, Marines came to Da Nang. Troop levels topped 200,000 people. B-52s start bombing Vietnam. 1968, there was the Tet Offensive. In '69, Nixon authorized bombing of Cambodia. In '70, Henry Kissinger and Premier Lee Duc-Tho begin secret talks. Nixon starts visiting China. However, we're bombing Hanoi and Haiphong with B-52s. Ceasefire signed in 1973, and then Nixon resigned, and Jerry Ford calls the Vietnam War finished. Last Americans leave Vietnam. So during that time period, as you realize, our B-52s were in danger, our F-4 Phantoms, our fighter jets were in danger. And so what was Ryan doing? Ryan had a wonderful field service engineering department. These guys went out and lived with the using command. We had authorization by the Air Force to do a quick response engineering program. You could redline drawings. You didn't need a lot of detailed documentation. As any of you who've worked with the military bureaucracy knows, contract data requirements list, configuration control, data management is the be-it-all, end-all for a lot of the bureaucracy. Ryan didn't really cater to that. If somebody in the field said we needed an airplane to do chaff dispensing, we would redline the drawings, we would put some Sergeant Fletcher tanks with reels of aluminum tape, shredders would drop the chaff down, the enemy radar saw just a big cloud, didn't know where the B-52 was. We did all that through field service engineering. As you can see in this picture, some of the drones had short wings for low altitude flights. I'll get into this a little later. Some had larger wingspans for the high altitude flights. And so we'll go back to the family concept. A lot of words on this chart. Let's just hit some of the highlights. I mentioned before Ryan owned Continental. Continental built an engine called the J-69. Many of you might have flown it in the T-37, but there was a drone version of that engine, non-man rated. We then authorized Ryan to build a slightly larger engine called the J-100. The J-69 had about 1,700 pounds of thrust. The J-100 had about 2,700 pounds of thrust. With those engines and the wing changes and the fuselage changes, we did high-altitude photo reconnaissance. We did electronic intercept. We did real-time surveillance with TV cameras in the nose of the drone. Low-altitude photo reconnaissance. There was a picture showing a North Vietnamese man on a bicycle looking very surprised as he looked overhead. The picture was taken by a Ryan drone. By mistake, they set the altitude to 45 feet instead of 450 feet. And this drone flew right underneath the bridge and right over this poor guy's head. We also had a decoy, and these drones could be equipped with a sulfur ball to augment their radar cross-section so they looked like a manned aircraft. The idea behind that is they had a sensor on board which could pick up the homing in frequencies of the SAM-2 and the SAM-6s. And before the drone was destroyed, these frequencies were telemetered back to a C-130 and back to a ground station, and the F-4s and B-52s set their jammers to those frequencies, so they were able to do their mission without fatalities. There was also a program, and I hesitate to use the word, but we dropped propaganda leaflets, and so these drones were called the bullshit bombers. Now, these drones were cheap, true to what their mission was. Again, according to the internet, they cost anywhere from $160,000 to $260,000 a piece, and that's a real bargain for you. The next slide shows a very famous drone, a high-altitude reconnaissance drone that did signal intercept. It did 268 missions monitoring North Korea. It used the Continental J-100 engine. The program was called Combat Dawn. It was developed after the EC-121 was shot down with the loss of all 31 crew members. Now, these drones had a system on board which we used to call hat rack bell ringer. And what that was the drone could tell if it was being painted by radar. And when that happened, remember these drones had big wings like a Schweitzer glider. The drone would go into a gentle turn. And now if you were flying a MiG-21, you were supersonic at altitudes like 70,000 feet. If you slow down, your afterburner would blow out, and then maybe your engine would flame out. So what these guys had to do to get to co-altitude and get off a shot was to convert kinetic energy to potential energy, zoom climb up, their engine might flame out, they would try to get to co-altitude and fire a missile at the drone, and the drone just went into a lazy turn. So it was a very clever, survivable tactic. Notice on top of the vertical tail, we used to call that a Kaiser helmet. Now, little round ball was a data link which would transmit real-time data back to a C-130. The next slide shows how these drones were launched and recovered. C-130 There were two C-130s operated by the 350th Strategic Reconnaissance Wing. They were based in Da Nang. They were air-launched from a C-130, and then a very brave helicopter pilot, suspending something that looked like a goalpost, would snag a drogue chute. The drones would come back to a rendezvous site. A drogue chute would pull out the main parachute. The helicopter would snatch the drogue chute and reel the helicopter up, hoping it didn't get into a pendulum effect, in which case a crew member with a hatchet, would cut the cable at the winch, and that would be the end of the drone. So it's a little complicated, but the guys were very successful in doing it. Here's a drone from an Aviation Week 1973, which had a homing bomb system, hobos, sometimes known as the GBU-15, the first smart bomb. This bomb had a TV camera in the nose. The drone also had a TV camera. The remote control pilot, sometimes flying on board a C-130, could steer the drone towards an enemy installation. The hobo video camera would acquire the target, and when the drone pilot knew the target was within kill range, the drone was within kill range of the target, he would fire the missile. And the bottom part of that slide shows the hobo taking out what could be a radar site for a SAM-2 or a SAM-6. Now, if you look at the bold print on the slide, it says that the tests were successful, but the Air Force officials saw these technologies as competing with manned aircraft, and so no funding came forward to pursue this. The next slide shows different configurations, drones used for radar jamming, reconnaissance, and weapons delivery missions. But all of these drones required air launch from a C-130 and recovery by a helicopter. One of the later missions was to drop acoustic sensors along the Ho Chi Minh Trail. And the picture shows some rather nice-looking sensors, but some of them look like dog poop, some look like rocks, some were disguised to look like things you might find in a jungle. And so they would pick up footprints or truck traffic and relay all that information back through a C-130 to a ground station so we could monitor traffic on the Ho Chi Minh Trail. Meanwhile, back at the Navy, to show it could be done, Ryan developed the Firebee-2. The interesting thing about this drone with the J69 engine is it could do Mach 1.6 without an afterburner. One of my friends, a guy named Harry Begg, designed the air induction system for it. Later, General Dynamics contacted him, and I think the F-16 inlet was based on Harry's design for the Firebee-2. Again, this target was used in developing the Phoenix missile, other air-to-air missiles. And to continue the Ryan story, what really got me motivated on this presentation was the history of 10 years of experience during the Vietnam War. There were 3,400 lightning bug missions flown against communist China, North Vietnam, and North Korea. The table shows how frequently these missions occurred. And the note, 578 drones of all types were lost. Half of these were shot down and the rest various incidents. The Chinese used the lightning bugs that they captured to copy, and so I guess the phrase Chinese copy was originated at this time. Okay, now, here's what got me to San Diego. It forced me to leave Hawthorne, California for La Jolla, which wasn't a bad trade. We had a requirement to fly over People's Republic of China and do it stealthily. And so in 1965, a photo reconnaissance mission was developed, high altitude. On the internet, you could see altitudes from 70 to 80,000 feet. The airplane had to be survivable. It had to have stealth characteristics, had to have low radar cross-section. We used radar-absorbing material, one of the first applications of RAM. IR suppression. We had no communications with the drone once it was launched. It had celestial navigation, pre-programmed flight path, and it was again air-launched by a C-130 and recovered by a helicopter. Here's a picture of the airplane called Compass Arrow. Next to it is a picture of the GE-1, the J-97 engine. This engine was under contract to GE from the Air Force Propulsion Laboratory, and they considered it their baby. They were very jealous about it. They were very protective about it. They weren't sure that these crazy people down in San Diego would take care of their engine, and so we had to mount a pretty good engineering position to show that we knew what we were doing. And so I was asked to work with GE on some wind tunnel tests, so we went up to NASA Ames, where, again, Ryan was a low-budget outfit, so I was the engineer working 24 hours a day for 3 days straight to evaluate what airflow might look like at the engine front face at different angles of attack, different yaw angles, just to be sure that the engine could live under those environments. And if that wasn't enough, we had a chance to visit beautiful Tullahoma, Tennessee in the winter. I don't know how many of you have been there. You stay in a town called Manchester. If you're lucky, you stay at the Holiday Inn. And if you're lucky, they still have the veal cutlet for dinner because that was the best thing they served. And so we were there for about 6 months, and we had a full-scale aircraft with a clipped wing. We had the J97 engine. We were running tests in the 16-foot wind tunnel. Now, you know they use Tennessee Valley Authority power, so you have to run from midnight to 5 a.m. Then you look at your data and you go home, you go to sleep, you wake up, do your laundry, you watch them whittling blocks at the county courthouse. That's what the locals did. You have your veal cutlet, and then you go to work. Now, at the altitudes we simulated, the air was so rarefied that the heat from the tunnel propellers made the air temperature too warm, was too hot. Remember, at these altitudes, ambient temperature is 64 below zero. So the engineers at Tullahoma had the idea of using freight trains coming up from Huntsville with liquid nitrogen, and they put manifold spray bars in that tunnel. And so they sprayed liquid nitrogen into that tunnel to cool the air down to get to realistic temperatures. Now, I got into trouble running this test. I was a troublemaker. The reason was the engineer on duty, John Harton, used to eat canned Vienna sausages at 3 o'clock in the morning. I don't know how he did that. John Harton said to me, "How do you want to end the day's run?" I said, "What do you mean?" He said, "Well, is there a data point you're interested in?" I said, "Yeah, people are wondering how high will this engine fly? So how about at every simulated altitude, we slow the tunnel down and watch the engine flame out?" He said, "It's a deal." And he did that. And I was okay until the Air Force Propulsion Lab found out that's what I was doing. Then they came down hard on my back. But later on, I'll tell you what they did with that data. So in summary, we built 28 of these airplanes. They never went operational. The stealth design, the configuration we used, is still in use today. And I'm glad to hear that the J97s were inventoried. They were not destroyed. So they may fly again in some program that you won't read about for quite a while. Now, the big change coming about after these drones was that the Air Force realized the cost per flying hour of the drone had to be factored by the cost of the C-130. And that wasn't just the airplane, that was the support crew, the guy that gave the crew member a haircut, gave him his lunch. All of those costs were thrown against the cost of the drone, and the helicopter crews. And so the Air Force said, air launch and recovery is too much. The logistical costs are too high. Let's look at something else. So they said, let's look at runways. So in 1971, a high-altitude, long-endurance program called HALE was written. The design goals for this airplane was something that could stay aloft for 24 hours, unrefueled, at altitudes above 55,000 feet. They wanted you to do runway takeoff and landing, and whatever the word contiguous means, they put into the request for proposal 20 cubic feet of contiguous payload. The competition, in fact, Boeing got their contract first, was Boeing with the GE J97 engine, the same engine that I tested at Tullahoma to see how slow you could fly it, and the Air Force chewed me out. They now gave all that data to Boeing, to George Bates, who thanked me later on for doing those tests. Now, and Ryan had the competing contract for the YQM-98A, which my boss, our program manager, Art Sullivan, called R-Turn, T-E-R-N, not T-U-R-N. Now, the difference in philosophy, Boeing builds manned aircraft, right? So they figured that the pilot has got to be in the inner stability loops of the airplane. The pilot's got to control everything. Ryan didn't build manned airplanes. And they said if the pilot's ass isn't in the cockpit, keep him the hell out of the stability loops. And so Ryan had a flight control system which handled all of the inner stability loops of the airplane. The Boeing airplane, which was heavily used fiberglass and composite materials, had what engineers call an aero-servo-elastic problem, which meant it took on a banana shape when subject to certain loads. So that vertical gyro, instead of pointing straight up, could point this way or could point that way. And so when the pilot was trying to manually land the airplane, it was a difficult chore. In fact, they crashed on, I believe, their first or second flight. So Ryan didn't do that. We had a digital autopilot. We needed an engine. I needed an engine that could do 24 hours at high altitude. To do high altitude meant you had to have a high pressure ratio. To do long endurance meant you had to have low fuel consumption. The answer is a turbofan. That's what everybody's flying around in today. There was this company up near the airport called GARRETT, and they had an engine that they were developing for the North American Sabreliner, the Sabreliner 60. It was called the ATF-3. I'll show you a little later a picture of the cross-section. It was a very unique engine. It had 3 shafts. It had a high pressure ratio, 26:1. It had a slim profile. It could run at high altitude. Had low heat exhaust, so it had a low infrared signature, and it was very economical on fuel. Here's a cross-section. Air would come in through the front, and about 1/3 of it would go through the core. 2/3 would go through the fan and be exhausted out the duct. The 2/3 of the airflow that went through the core went through the low-pressure compressor, went straight to the back and turned 180 to go through a radial compressor, which gave it a 2-to-1 boost in pressure ratio, made another 180 go through a combustor and through a high-pressure turbine, and then came back out through the low-pressure turbines, and another 180 to come out through 8 exhaust hoods. So I think if you don't get lost or don't get dizzy, it's 360 degrees of turning. Now the advantage to that is that the hot air coming out from the combustor was mixed with the cool air coming out from the fan. 3 parts of cool air to 1 part of hot air, which meant that the IR signature was very low, very cool exhaust coming out. All of the accessories were hooked on the back end of the engine, which meant there was a slim profile. And we were lucky that there was a nacelle to house this engine that was built for a Paris Air Show. There were 3 engines in existence, 15, 16, and 17. We took them all, and we took the nacelle from the Paris Air Show. And with that, in 1971, as my memory serves, we were given $13 million and told, go build 2 prototypes, and you can specify government-furnished equipment for stuff. No spares, no money for spares. We found that the T-38 had landing gear we could use, and the Canadian CF-5 had a nose gear we could use. And since we did automatic landing, we found the Marines had a tactical landing radar system called TALAR, which we could use to line the bird up with the runway and help with landing. The wingspan on this airplane was 81 feet. At takeoff, it weighed 14,300 pounds. Zero fuel weight was 5,000 pounds. Next slide shows a picture of Compass Cope. It was ferried from Lindbergh Field to Edwards Air Force Base on a C-5. It was a lot of fun at lunchtime walking out to Lindbergh and watching that C-5 come in and load up our drone and take it out to Edwards. The airplane, as I mentioned before, had digital flight control. So it had a takeoff mode, a climb cruise mode, a descent mode, and a landing mode. Boeing, as I mentioned, had a TV camera in the nose. The next slide shows the airplane in flight. We'll talk about some of the subsystems. You can see that the engine is shielded by the fuselage. The fuselage has the same shape as the compass arrow. We used parts of that structure for this airplane. It was a new wing, however. The twin vertical tails shadowed the exhaust from anybody coming up at you from below or even at co-altitude. The airplane carried the payload in the nose. we needed high reliability for a 24-hour flight. And the secret of doing reliability is that the more redundancy you have, the better the reliability in case something fails, but the more chances you have of having something to fail. It's like wearing a belt with suspenders. What are the chances that both will break at the same time? And then we had to keep costs down, so we had dual analog systems for pitch, roll, and yaw, but we had a roam computer, a digital computer, to do monitoring. So if pitch sensor 1 said you were in a dive, and pitch sensor 2 said you were in a climb, the digital computer, knowing what you should be doing, would say, okay, you're wrong, and shut you down. So we had redundancy by each axis. It did have a radar altimeter on board, and when the drone got to within 70 feet of the runway, it did an automatic flare and rate of descent, H-dot versus altitude to a landing. It had a microwave command guidance control system. It had a UHF backup link, and we had a U-2 out of Patrick Air Force Base fly chase. One interesting story, if you've ever been to Florida, you know they have all these wonderful birds that go out and find clams and hard-shell things to eat. And the way they eat them is they drop them on the runway, and they crack open. Then they come down and they eat them. And so our drone is getting ready to take off, right? And so the range safety people they couldn't tolerate this. Here are all these birds. So they sent a fire engine down the runway to scare the birds. And here comes a guy named Dave Bittenbinder flying our 2-seat U-2. He's flying right overhead at low altitude as all these birds go straight up in the air with the fire engine siren going. So Dave gets on his link and says, stop that. And so we stopped that. So now the birds are out there on the runway. The ATF-3 cranks up, goes to intermediate power. The bird starts rolling down the runway. These birds aren't stupid. They see the drone coming. They just waddle out of the way. The drone goes by and takes off. The birds go right back to finish their lunch. So it was kind of nice to watch nature at work. So now we had we thought a successful program. So I was asked to put together a proposal to the Air Force to productionize this airplane. And if this looks like the Global Hawk, it's intentional. We put together a Plan A, so you could see we could fly in mid-1977. The next slide shows the combat radius of action. SAC pilots, Strategic Air Command pilots like Diego Garcia. We had one in our sales department, so we based the airplane at Diego Garcia, and you could see we could fly out even to Antarctica and stay 2 hours on station with that airplane. There was the Gulf of Tonkin in the Philippines. But in spite of all that, in spite of the fact we flew 17 flights, 90 hours, one of our flights lasted for 28 hours and 11 minutes unrefueled. And again, a little story. There was an Air Force captain, Dan Stamp, who was in charge of monitoring our flight test program. He flew in from Dayton down to Florida. We were there at the telemetry station. How you guys doing? Well, we're doing great. Where's the airplane? It's at 57,500 feet. He had a fit. He said, turbofans can't fly at those altitudes. Bring it down. We said, yeah, well, we're okay. Bring it down. Well, we had spoilers. So we started using spoilers. And so as we set this record, I think the last 8 or 10 hours had the spoilers continually going up to keep the airplane from flying higher than the Air Force captain wanted. So we did all that. The FAA regional in Atlanta was able to give our drone controller commands, steer left, steer right, because that corridor between New York and Miami is heavily trafficked. And so they wanted to be sure that a drone like ours could evade manned aircraft. And so we were able to do all that. We demonstrated a payload. Remember B.B. Rebozo, President Nixon's friend? Well, we took one of our drones and we had a payload in it. I don't know what it was, but they had vans with these big guys in uniforms wearing white helmets, white boots, and carrying machine guns. And we were told, don't go into the van and don't ask them what they were doing. So we were very careful not to do that. And our bird flew down off Florida and close to Cuba. And I think they were happy with what they got, but these people didn't talk to you. The program was terminated, and we were told, however, that Boeing was going to be the winner of a production contract. And we didn't like that. So I was the engineer. I was told, pack up your data. We're going to go to Washington, to the Sam Rayburn building, and we're going to sue the U.S. Air Force. And so we took Congressman Bob Wilson from San Diego, the president of Ryan, and me, and we went to the Rayburn building. We took on the Judge Advocate General. We took on the Air Force. We said, we should have won. And so the Air Force later found that they upheld the Boeing contract, but then they canceled the contract and disbanded the drone SPO at Wright-Patterson Air Force Base. And so drones died with all that event, and I decided I better get the hell out of Ryan. We had one customer, the Air Force, and we sued him. So that's when I joined GARRETT. That's what got me back to California. The next slide shows 1,000 airplanes were built back in the 60s to the 70s, and it was a period in history that was very exciting for me and I think for our country. The next slide shows, by comparison, the Q2C started out with about a 10-foot wingspan, compass cope, 50-foot compass arrow, 50-foot wingspan, and compass cope, an 80-foot wingspan. And the next chart shows, from a propulsion standpoint, the original J69 and the Q2C at 1,700 pounds of thrust, the J97 at 5,000, and for the heck of it, I put the Global Hawk down at 7,000 pounds of thrust. So now, time marches on, and where are we today? Notice the bottom right of that slide shows that the Global Hawk, $35 million each, the last I checked. That makes our $13 million contract to build two and go fly seem like chicken feed. Uses the Rolls-Royce Allison engine, 116-foot wingspan, 22,000-pound takeoff gross weight, and they are big budget items today. The next slide shows the Predator drone, which we're all familiar with. The bottom of the chart says that as of March 2011, the Air Force was training more pilots for advanced unmanned systems than they were for any other single weapon system. That's how far drones have advanced today. And of course, finally, we have the capture of the Sentinel. And the last reports I heard, the Iranians are claiming they were able to hack into the GPS coordinates and fool the drone into thinking it was landing in the site it was supposed to land at. And so we don't know what happened to the undercarriage. They said that the altitude for the landing site was different than the intended altitude, so maybe there was a problem there. So it only took 45 years from San Diego to the UAVs of today. Go back and remember that target drones were the pioneers. The budgets had to be affordable, don't compete with manned systems. Vietnam said that we needed new missions and new sensors. GPS is here today. Whether it stays based on the Sentinel experience or not, I think we got to do something about GPS. Runway takeoff and landing is common. In fact, the Army with the mini drones are able to have handheld launches. Vehicle size today dictates man-rated propulsion systems, and I don't know if pilots are still reluctant to accept these things. They are around. My final chart sort of takes a look in retrospective of Ryan. I'm using the 350th Strategic Reconnaissance Squadron patches as a tribute to these guys. Ryan was a single product company. They lived or died by what the Air Force wanted to do with drones. You know, your word was our command. We had only a few thousand people, maybe 400 engineers. They also were the logistical support center for spares, replacement parts for our drones. We had minimum paperwork. Tell us what you want, we'll redline the drawings, we'll get it out there, and we'll fix it for you right away. We had remote pilot experience with autopilots. We could do flexible mission programming, great field service engineering. And looking back at my 41-year career, I think it was the 10 most happiest years of my life. I was also a lot younger, of course. Thank you very much. The question is, where can people go to see a Ryan drone? Well, here we are at the Western Museum of Flight, and right outside our meeting place is an exhibit where you can see one of the Ryan reconnaissance drones. It was a low-altitude photorecce. It's painted black, and it's worth taking a look at. Question is, what are spoilers? Top of the wing, they have devices, panels, which come up and spoil the airflow over the wing so the airplane comes down. When you're landing, look out the window and you'll watch the spoilers come up on the Boeing airplanes or Airbus.
This is the YQM-98A, an Air Force high-altitude, long-endurance prototype RPV. This is its first flight. The flight controls are being monitored by an onboard mini-digital computer. This computer is capable of being programmed to perform an entire mission profile. The RPV has sufficient redundant systems, both airborne and ground, to assure the mission reliability the program requires. Let's look under the skin. A good place to start is flight control. There's total dual redundancy: control actuators, gyros, sensors, and control electronics. All dual, all with onboard computer-programmed switching. Redundancy is equally apparent in the electrical system. DC generators backed up by dual batteries. The AC inverters backed up by an AC generator. The landing gear and brake hydraulics have an independent pneumatic backup system. In command link, the redundancy becomes quadruple: 2 separate MCGS systems, plus dual UHF systems. Any one of these 4 links can fly an entire mission. The prototypes are powered by a new GARRETT ATF-3 engine with very low fuel consumption, low noise level, and is relatively smoke-free. But this RPV program started back on the drawing board in June of 1972 with the YQM-98A design effort. 18 months elapsed from award of contract until simultaneous rollout of the 2 prototypes. Then 3 months of intensive training with computer simulation of vehicle flight dynamics and the interface with MCGS stations, UHF station, and telemetry van. There was hands-on training for runway controllers using a King Air 90 equipped to receive MCGS and TAILAR data. This provided dynamic landing approach simulations for the alternate semi-automatic and manual landing modes. Here, the controllers make glide path adjustments by means of a bore-sighted television monitor. Such simulations were also run at night. The 2 RPVs were transported from San Diego in an Air Force C-5A. By the end of April, both the flight test crew and the RPVs were at Edwards Air Force Base. There followed 4 months of vehicle and support equipment buildup, taxi tests, checkout, and calibration. And on the 17th of August, 1974, the successful touchdown of the YQM-98A first flight. The major flight test objective was this long-endurance flight, which will span more than 24 hours. It's 5:30 a.m. on the desert at Edwards Air Force Base. The vehicle and its ground equipment have been pre-flighted. The onboard computer begins its check. Using aircraft power, the mini-computer rapidly checks all primary and backup flight control systems. In just 20 minutes, final verification is received on what could otherwise be a one-day manually performed system check. As the ground stations report a green status, control of the YQM-98 is handed to the primary runway controller. Umbilicals disconnected, chocks pulled, brakes released, and throttles advanced. In less than half a minute, the vehicle is airborne, climbing in its takeoff mode for about 3 minutes. At that point, control is handed from the UHF controller to the primary MCGS van, which will retain basic control through the entire cruise mission. However, the entire mission from takeoff to landing could be controlled from either a UHF or MCGS control station. Safety chase is provided by a U-2 for the first portion of the mission. The cruise climb section of the mission to the mission altitude is routine. Once mission altitude is attained, any additional climb will be the result of fuel burn-off. The primary MCG command and control van records vehicle condition on a continuing basis. Also, the ground track of the flight is recorded on an XY plotboard. A similar record is being acquired at the Edwards Flight Test Center telemetry station, 79 channels of real-time downlink instrumentation data. There is an additional independent telemetry van adjacent to the primary MCG control van, which monitors on continuous reading meters 20 pre-selected flight parameters with instant alarm indicators. 48 channels of real-time brush data are also recorded in this van, as well as all 79 channels on magnetic tape. This provides both on-site quick-look data and permanent detailed records for post-flight evaluation. The routine of the long-endurance flight has set in. 4 hours have already elapsed, and the crews are being changed. This 4-on, 4-off pattern will continue through the day and night. High above the California desert, the YQM-98A flies its prescribed course, its computer ready to instantly switch to a redundant mode in the event of an out-of-tolerance condition. Another crew change as the flight continues. All systems still go. The mission has been planned to keep the vehicle within glide distance of the lakebed runway, so that if an engine malfunction occurs, a successful dead-stick landing can be made at the takeoff site. This is the final crew change, and there is an air of excitement starting to build. This crew will land the vehicle. The throttles are reduced to idle. The planned landing sequence has begun. 30 minutes from now, touchdown will occur. The U-2 rejoins for descent and landing. Should a quicker descent be required, landing gears and/or spoilers can be deployed, which will cut the descent time from altitude to a minimum of about 8 minutes. When the RPV arrives at 5,000 feet, landing mode enable is engaged, thus making the vehicle receptive to landing commands. The vehicle is directed for a landing approach. Spoilers, now closed loop, are automatically deployed until an altitude of 4,000 feet AGL is reached, and then that altitude is maintained. Then, at the correct predetermined point, the vehicle goes into a nominal 13.5 foot per second rate of descent, a 4-degree glide path. This descent can be adjusted either by the onboard computer or remotely by a ground controller. 3 distinct landing modes are possible. The most automated uses TALAR, Tactical and Landing Approach Radar. If TALAR is invalid, a TALAR inhibit command reverts the flight control system automatically to semi-automatic approach mode. In this mode, the onboard computer uses radar altitudes to maintain the vehicle on the glide slope. Azimuth control is maintained through the automatic heading hold mode. Crab angle for approach is established by remote heading slew commands. The flight control system roll axis maintains wings level. The third system, manual landing mode, can be actuated by the flight control officer, giving him sole control of the lateral and vertical path of the vehicle through the remote control command links. During a tail-hour landing, a runway-mounted multi-beam microwave transmitter sends signals to the vehicle as it is on final. 4 bore-sighted beams are received, 2 for azimuth control, 2 for elevation control. The beams are processed by an onboard tail-hour receiver, which in turn outputs azimuth and elevation glide path error to COPAR flight control and computer systems. A second tail-hour transmitter provides for automated lateral steering controls during landing rollout. 70 feet above the ground, the radar altimeter signal automatically initiates flare by commanding a 2-degree nose-up attitude and a 2 foot per second rate of descent to touchdown. Tail-hour is deactivated at flare. 15 feet above the ground, a decrab maneuver is automatically commanded by the radar altimeter signal to take out any vehicle yaw due to crosswinds. Touchdown occurs with the vehicle nearly aligned with the runway. Control system logic commands the elevators full down to depress the nose and fully extends the spoilers to increase drag and decrease lift. During rollout, the second tail-hour, located at the end of the runway, provides azimuth-only steering commands. At approximately 75 knots, the brakes are manually applied. The rollout completed, and the engine shuts down. The outstanding success of this high-altitude, long-endurance flight completed the major objectives of the flight test program. Thus, the frontiers of aviation technology have been rolled back a bit further by this Air Force RPV program.
Thank you for watching Peninsula Seniors Out and About here at the Western Museum of Flight in Torrance. I'm Betty Wheaton. I'll see you next time.